Hello, we are Team PK Squared, and we are the Car Head Tracking Senior Design Project. We are team number 33. I am Patrick Schwartz, and I'm in charge of the microcontroller algorithm subsystem.
Hi, my name is Koksin Tan, and I am in charge of the face and eye tracking algorithm for this project.
Hi, I'm Callie Lacey. I'm in charge of motor movements that will be in the system.
Hi, I'm Patrick Betts, and I'm in charge of the power module that powers the entire system.
So basically what our project is it's an algorithm that will take a reading or a picture from a camera and determine the location in 3D space and find the location of the person's eyes, the midpoint of it, and determine where or what position the motor of a car mirror needs to be adjusted to allow the driver to see behind them properly. All right, and now the other three members are going to go over what the requirements for our system are.
So the first requirement for this project is that the tracker will sense the location of the user's head when the button is pressed. And the second requirement is that there will be a dual camera system integrated into this project.
The algorithm will determine the standard location of the driver, and then there will be a target behind the driver in the view of the mirror. And then servos will be able to move the mirror to a specific location to determine the location from the earlier requirement.
And requirement number 4 is that the system will be powered by a car battery alternator. We only have a battery, so it's going to be powered by a battery simulated at 12 volts. And the 6th requirement is that the motors will be able to track the location that the mirror is in currently.
And then now we will begin to show you a demonstration of our system at work.
Hi, my name is Koksin, and I am in charge of the head and eye tracking part for this project. Here is a brief overview of what my subsystem is supposed to do. So first, it detects where the driver is in position in the car. And that can be done by, let's say, having a pressure plate underneath the driver's seat, or having the driver do a certain action, such as starting the car. So basically those actions you mean that the driver is already in position. And I will be simulating that by having a button right here. And once this button is pressed, it basically simulates that, oh, there's a driver in the car and I should start this Raspberry Pi right here. And then once this Raspberry Pi is started, it runs a script that runs this program right here. However, I can't demonstrate my subsystem to you right now because when I hook up my subsystem to the power system subsystem on Thursday to integrate both of our subsystems together, I think there is a design flaw in the power source system that results in an overcurrent, which means like an excess current being sent to this board, and as a result, the this board is currently not functioning right now. So as a result, I moved everything to my own Raspberry Pi in order to make it for this midterm demo. However, on Saturday, I realized that the camera is not working once I re-downloaded everything into my own Pi. And I tried this camera with my own laptop as well, and it doesn't even detect that a USB device is inserted. So I think this camera is not working right now. However, I can show you a few pictures to show that I actually made progress in doing my subsystem. So basically, when it captures a frame, it finds a face and then draws a square box around it, and that face is found using a deep neural network pre-trained model. And that is because it is much faster as opposed to let's say a feature-based detection algorithm to find a face, such as a hard cascades algorithm. So that's why I defaulted to using a deep neural network. So once it quickly finds a face, it needs a more precise algorithm to find the eyes, and that's where the feature-based eye detection algorithm comes in. So I use a DNN to find the face, and then use a feature-based algorithm to find the eyes. So the deep neural network algorithm bounds the face, and then it constrains this space for the algorithm to find the eye. So it minimizes the error from anything that resembles an eye outside of this square bracket, and makes it much more accurate and much faster. So if it gets the eye, it finds the midpoint, and then that will be the x and y coordinates. If it doesn't find the eye, it will find the midpoint of that square box, and then output that as the x and y value instead. And then there's also another feature that I implemented, that if it detects multiple faces, it will find the face that is closest to the driver, which means that the biggest box, because it signifies that that face is the closest to the driver. As you can see here, the red is being detected. So it detects both faces, but red is the one that's being chosen because that is the one that is the closest to the camera itself. And then that is outputted to this thing right here. So it captures 5 frames, and then as you can see here, if first it finds the midpoint because it can't detect the eye, but the subsequent 4 frames are using hard cascades because it can find the eye, and then it outputs the average x, y, and z coordinates, which is then sent as a UART signal. So I can demonstrate that to you quickly right now. So when I run this, it outputs a UART signal, and then it outputs the x, y, and z coordinates respectively, and then that will be sent to the subsystem that Patrick Schwartz is in charge of, so that it could use these 3 coordinates to calculate the optimal location of the mirror. So my subsystem is essentially done, if not for the board being fried and the camera as well. So now I think that we need to purchase a new board and probably a new camera as well, to make sure that the project works. But otherwise my subsystem is almost done, except for the PCB designing part. Thank you.
All right, I'm Patrick Schwartz, and my subsystem on this project is the microcontroller algorithm. So the first part of the algorithm that I'm going to show is the part that takes in a UART signal from Coxon's subsystem and turns the string numbers, or the string of numbers that it gives me, and turn it into an x, y, and z location, and then calculates the angle that the mirror needs to be at in order for the person with eyes at that x, y, z location to be able to see properly in the mirror. So the first things first, here are the 5 variables that I'm going to keep track of through the debugging process. So it's IX, IY, and IZ, which will be the X, Y, and Z values that I get from the UART system, and X angle and Y angle, which are the calculated values of the angle of the mirror that needs to be at in order to provide the right view in the mirror. So right now these values don't really mean anything, they're just there. But what I'm going to go ahead and do is run the code, and then I have here my ADLM2000 connected to the PA3 pin, which is what I'm using to read in the UART signal. I'm going to give these string of numbers to the system. I'm going to go ahead and run single, and it will calculate, or it'll go ahead and send that data to the program. And here we are, there are those values stored in the X, Y, Z. And then those other 2 numbers for the X angle and Y angle are the angle in radians that the mirror needs to be at in order to run. So now what we're going to do is I'm going to demonstrate a different part of the code. This part of the code takes in a voltage reading on the microcontroller, and depending on what that voltage is, it'll turn PC8 here either on or off. It's a LED light bulb there. So if the voltage that it reads on pin PA1 is greater than 1.5 volts, it will turn on. If it's less than 1.5 volts, it'll stay off or turn off if it's already high. So I'm going to use the ADLM2000 to give it a voltage level. So currently the voltage is set to 0.5 volts, so it is off. And then I'm going to go ahead and bump it up to 2 volts, and the light turns on because it's above the threshold. Then it goes, bump it back down to 0.5 volts, and it turns off because it's below the threshold level. So basically what that does is it demonstrates that that by taking in a voltage on a pin, it can output a voltage high or low depending on what needs to happen to the different motors. And then later on in Patrick Betts' subsystem, where he talks about the motor controller, we have the microcontroller actually plugged in to prove that when the microcontroller pin goes high, it will actually move the motors as we designed it to. So yeah, on to the next subsystem.
So I was responsible for the motor movement outputs. and we wanted to read the current position so that we know where we need to move it based on the current position. So I wrote a code that will update the readings and the values. So you can see the values are updating rapidly. So we know that we're getting the appropriate values at the time. And we double verified with the DMM to make sure we were getting the same measurements, to make sure that my code worked. And also right now we're working on trying to develop the voltage regulation system. And it's working some, but it still needs some work. But our goal is to get that for the microcontroller to only accept 4 volts. But it's just in case, because the mirror needs 3.3, so we have to stay under that. We don't want to fry the microcontroller because it's expensive.
My name is Patrick Betts, and my subsystem is the power module. In the power module, we're using a 12-volt battery to simulate a car battery. I output from the 12-volt battery, step down through a voltage regulator into the microcontroller, 3.3 volts, and to the Raspberry Pi, 5.2 volts. From the microcontroller, goes into the motor driver, which is also part of my subsystem. We have 3.3 volts here and 12 volts here to power each side of the motor driver, which powers the motor essentially. All of it is connected, so what should happen is it goes from the battery to the micro will run the mirror. As you can see, the mirror is running. We have it set to do each side of each motor, so it goes in a circle basically. As we can see, we are outputting 3.3 volts here approximately for the microcontroller, and about 5.2 for the Raspberry Pi.